Hi, let's now move on to the fourth block of Module 2 Electricity Spot Market, which looks at zonal and network aspects. So far we've discussed market organization, auctions, market clearing, settlement, but we've considered that we had a single market where everybody was represented, both supply side and demand side. We mentioned the system price, which is a single price coming out of the market clearing. And if you go on the webpage of the Nord Pool and look at a snapshot for the market clearing, let's say for a given hour, a given program time unit, you will find the system price. For this example, day and hour, the system price was only 4.59. It was the 14th of October 2018, between 6 and 7 in the morning, and the currency is euro. If zooming in on the various countries here, we don't see this value of 4.59. In northern Norway, which is the area NO4, the price is at 37.87. Looking at all these areas here in between, Sweden and southern Norway, the price is 4.06. Looking at Denmark, on the eastern side of Denmark, DK2, the price is of 22.07 euro per megawatt hour. So first of all, we see that in a market, the prices may vary geographically. And this is what we want to understand and describe in this block of Module 2. The reason for that, remember, is that there's a network involved with certain capacities for the various cables that form this network, and power has to flow and respect some of the physics of power flows, and there might be also some reservation in terms of the network and assets for contingencies or some security consideration. So far, we have not accounted for this physical limitation related to the networks and to operations, and these are the reasons why the prices may vary geographically. There are exchange capacity limitations from some areas of Scandinavia, if looking at the Nord Pool, to some others. Here for the various areas, again, if you go on the website for Nord Pool, looking at a certain day and at a certain time, so a certain market clearing situation, you can be shown little arrows between different areas, and for each of these arrows, they are double-sided arrows, you have two numbers appearing, which is the quantity of energy which you may be able to push from one area to the next, or the quantity of energy you can push from the other area to the first area. These capacities can vary from hour to hour or day to day. Obviously, fundamentally, the cables are there and they have their physical limits, but as mentioned earlier, those limits may be varied depending on the situation of the system, some security consideration, and how much may be reserved in case of contingencies. So we have capacities which represent the maximum amount of energy that can be pushed from one area to the next. What happens if we reach this maximum amount? We cannot push more energy from one area to the next. We then talk about congestion. And when we have congestion, the prices will become different geographically. This is what we're going to discuss now. These exchange capacities are related to the network constraints and operational practice, which is now what we want to integrate also in our market clearing. There are different approaches to handle these exchange capacity limitations, and often we say fundamentally the difference is like the European view and the Northern American view. In Europe, we have a system operator, which we call the transmission system operator, taking care of the higher voltage level for the power system related to the wholesale market we care about. And we have a market operator which is independent. We mentioned Nord Pool, for instance, for Scandinavia. In the US, this role might be covered by the same agent, the independent system operator, which may be taking care both of system operation and also market operation. In terms of the market itself, the offers, which we discussed extensively in previous blocks, relate to certain type of market products. We focused on the most current market products, these quantity price offers. There are other market products that could be considered, making the problem more complex. But still, we focus on these market products as the basis for offering in the market. In Northern America, or following this philosophy coming from Northern America, what we offer is actually unit capabilities. So you declare what your generator, for instance, could do, and then the system operator will integrate that in some optimization problem. So having a finer description of what the assets can actually deliver and under which constraints. Here we're not really sure of what you're using as a generator. If you supply energy, we just accept that you've made this offer, maybe you're going to be scheduled, and then you will self-dispatch, meaning that you will figure out how you're going to deliver. For the clearing, we discussed this supply-demand equilibrium. So we have this basic economic concept, supply has to meet demand. We want to optimize, maximize social welfare, but it's based on the simplistic or simplified representation, better to say, through market products. Under the Northern American philosophy, we have a full unit commitment and economic dispatch problem, accounting for all the unit capabilities, and this is therefore a more complex, a more complete optimization problem that will be able to give all the schedules for the units, the set points, etc. In terms of the network, in Europe we have a fairly simplified representation of the network through these capacities that I showed in the previous graph. From one area to the next, we estimate we can exchange this amount of energy in one side and the other, but it's fairly simplified. In the US, or following this Northern American philosophy, you go for very detailed representation of the network so that you really understand what's going on with the network, its potential operation, and this is directly accounted for in the optimization problem. While here, what we will discuss is that we simplify this exchange capability, and that simplifies also the solving of the optimization problem. Eventually, in terms of prices, in Europe, since we only define these areas and capacities for exchange between areas, then we will define one price per area or one price per zone. And this is why we call it a zonal electricity market. Following this philosophy, since we have a very detailed representation of the network, we will end up with having a different price for each and every node of the network. Therefore, we call it nodal pricing or nodal electricity market. You may look at illustrations of this concept and what happens then. If you go for Scandinavia on the website of Nord Pool, where you can look at maps of prices, exchanges between areas, etc. for each and every day, each and every program time unit. Similarly, if you go, for instance, on the website of Midwest ISO in the US, you can look at a representation of this nodal pricing. On this map, you have some color contours, and for each of the colors in this code, you have different ranges of prices that are there for the nodes of the network. So how does that work in practice? For discussing that, we're going to revisit our previous market clearing example. Remember that we said that all the suppliers and consumers were in the same market. Sure, they are in the same market, but now let's say they are on two different areas, two different sides of DTU. We're going to call them DTU West and DTU East. So we need to localize this supply agent and this demand agents. On the supply side, we're going to place G1, G3, G5, G7, G8, G9, G10, and G12 on the DTU West side. For demand, D1, D3, D5, D6, D8, and D9 are going to be placed on the DTU West side. On the DTU East side, for supply, we have G2, G4, G6, G11, G13, G14, G15. Obviously, there are those who are not on the west side. Same for the demand. Those who are on the east side are D2, D4, D7, D10, D11, and D12. Why is it interesting to consider two sides? Because we're going to have some limited capability to exchange energy between the two sides. In terms of power, we can only exchange 40 megawatts between these two sides, and since we have program time units of 1 hour, this means that we can only exchange 40 megawatt hours per hour between one side and the other. So we have to see if this limitation is going to affect our market clearing now. Let's localize the offers we got from the previous blocks. Remember all the companies, Clean Retail, L4U, EV Charge, and their offers in terms of an amount and a price, but now we have added the area that the offers belong to. Some of the offers are made on the DTU West side, some of the offers are relevant for the DTU East side. Same for the supply. We have offers that are relevant for DTU West and DTU East. Note that we have the same list of companies, same list of offers, and that for some companies, maybe they could have some offers on the DTU West side and some offers on the DTU East side. Since these offers are not obviously localized, the company could have assets in different areas of the power system, so you could make an offer on one side and an offer on the other side as the same company. Only these ideas, these unique ideas count, not the company that covers the portfolio itself. Now let's localize the previous market clearing results. We got our market clearing, we got a schedule for each and every supplier and consumer in the market. Let's see if they are on the west side or on the east side. On the supply side, G1, G3, G5, G7 and G8 are on DTU West, and they represent a total of 495 megawatt hours that's going to be supplied through the market. For demand, D1, D3, D5, D6, D8 and D9 are on the DTU West side and are scheduled through the market for a total of 555 megawatt hours. This means overall, on the DTU West side, the demand is going to be higher than the supply, and the difference between the two is of 60 megawatt hours. We call it a deficit of 60 megawatt hours. Eventually, this means that we would like to import or to bring some energy within DTU West to cover this deficit. Looking at the other side of DTU, DTU East, for supply, G2, G4 and G6 are being scheduled, which represent a total of 500 megawatt hours. And for demand, D2, D4 and D7 are scheduled for a total of 440 megawatt hours. Logically, if we had a deficit of 60 megawatt hours on one side, we have a surplus of 60 megawatt hours on the other side, since overall we have a balance, supply equal demand. So we have a deficit here of 60 megawatt hours. We have a surplus on the other side, DTU East, of 60 megawatt hours. They should just exchange. We have these limitations though, that only 40 megawatt hours can flow between the two sides of DTU. If only 40 megawatt hours can flow, we have congestion. Not all the energy is going to be exchanged. This is going to create some problems, you could say, but we could account for that readily in the market clearing, so as to account for this limitation right away when scheduling the various suppliers and consumers, and also when finding the price at which we should settle these various exchanges. Let's go first through the basic intuition, and this basic intuition can be expressed through an import and export approach. We localized our supply and demand offers, supply and demand schedules from the unique market clearing. Since we have two sides in the market, maybe we can actually split already and set up two market clearings. We could define a merit order, define a supply curve on the DTU West side. The demand curve here also is there with only the demand offers on the west side. And we will see an equilibrium point appearing for DTU West. For DTU East, we do the same thing. We define a supply curve respecting the merit order with only the supply offers on this side. And for the demand, we only take the demand offers from this side. We follow the merit order on the demand side, and we can define here also market clearing with an equilibrium point, and you could deduce a schedule. We are still missing something here, since this only corresponds to the offers on the supply and demand side. But we said we have also this capability to exchange energy between the two sides. We have these two clearing points, and the value of the price, so the market clearing price at these two clearing points on DTU West and DTU East, is important to define how we're going to consider this transmission capability. In our case, we have a high price area and a low price area. Most likely, you will have this situation that in one side, if doing the market clearing, the prices is going to be higher or lower than on the other side. There is this basic rule that power should always flow from the low price area to the high price area. Obviously, on the high price area, it means there are more people who are ready to pay a higher price for this energy, and on the other side, there are people ready to sell at a lower price for this energy. So we can increase social welfare by matching this extra supply and demand. On the high price area, we can then have extra supply, and this extra supply is actually coming from the other side through the cable. So we have 40 megawatt hours that is an extra supply offer, and it's prioritized. It comes first. So it comes at the lowest price in the market. Here the lowest price considered is 0, so we have this first 30 megawatt hours, 40 megawatt hours that represent the cable, you could say, related energy that comes into DK West. And on the other side, we do the same, but it's an extra demand. It's not an extra supply. So DTU East has an extra demand of 40 megawatt hours, which is actually the demand coming from the other side, from DTU West, and will come first. So we have this extra block of energy on the demand side that comes first, so at the highest price in the market, and here of 40 megawatt hours. Now, our two figures here are complete market clearings for the DTU West side and the DTU East side, since they represent the basic offers, but also the extra energy that will be exchanged between the two areas. We can now clear these two markets side by side and obtain the schedules and the prices. We can also do it as an optimization problem for each side individually, so as to illustrate what is going to happen. On the DTU West side, on the supply side, G1, G3, G5, G7 and G8 are schedules, but here the schedule of G8 is different from before. The schedule of G8 was 55 before, now it's 75 megawatt hours. The total of supply on that side is 515 megawatt hours. On the demand side, we get the same schedule as before, with D1, D3, D5, D6, D8 and D9 being scheduled for a total of 555 megawatt hours. The difference between supply and demand is now 40 megawatt hours, which seems to be our goal. We want to only have this deficit of 40 megawatt hours that should match a surplus of 40 megawatt hours on the other side. In terms of price, at the clearing between supply and demand, the price is the same as before. It's 37.5, since it's the same offer that is marginal and setting the price. On the other side, on DTU East, on the supply side, G2, G4 and G6 are being scheduled, but only with 30 megawatt hours for G6. So G6 is becoming the marginal supplier on the east side, and is going to set the price. The total here is 480 megawatt hours. On the demand side, D2, D4 and D7 are being scheduled for a total of 440 megawatt hours. You can recognize the surplus of 40 megawatt hours, and now at the crossing, based on G6 being the marginal supplier, the price for this area is of 34 euro per megawatt hour. So you see, we end up having satisfied the physical constraints, having deduced the resulting schedules that respect these constraints, and obtaining some prices based on this local matching of supply and demand which end up not being the same. In terms of settlement, which we'll discuss afterwards, each and every agent has to get the price or pay the price of its own area. We can handle this problem more elegantly through flow-based coupling, which is the way we couple all the areas in the European electricity market. We have a power system with DTU West side and DTU East side, some demand, some generation, and an exchange capability with a cable of 40 megawatts between the two areas. We can write off our market clearing problem still with social welfare maximization, but now we're going to respect the fact that we have two sides of the power system. Instead of the single balance equation we had previously, we now have two balance equations. These are here the balance equation for the west side, and here the balance equation for the east side. In both cases, this balance equation should represent the fact that the sum of consumptions minus the sum of generation is going to be equal to either the import or the export capability for that area. And these are given here, and the reason why it's formulated this way is that this import-export capability should respect the physics of the power system in terms of susceptance and difference of voltage angles. Here in this simple case, we end up having the value of 40 for our illustrative example, but in more complex example, you may have exchange capabilities that are more refined depending on the power system characteristics. All right, in terms of zonal prices, now that we wrote this optimization problem, this linear program with two balance equations, remember that the market clearing price, the system price, was related to the dual of the single balance equation we had before in our market clearing. We now have two balance equations, which means we have two Lagrange multipliers or prices related to these two balance equations. In the rest of the formulation, the inequality constraints are the same for the set points in terms of consumption and generation, and we also have this extra inequality constraint such that the exchange between the two areas can be between minus 40 and 40, meaning it's actually between nothing and 40, but either in one side or the other. If we apply this optimization problem to our illustrative example, we can directly model everything from the start. We have all the offers in terms of quantity and price, we have the physical limitation, and by solving this problem at once, we can get the schedules and the prices on both sides. These are the results that we get. They are obviously the same as with our intuitive example with import-export explanation of how this could work. But the advantage is that we do that from scratch all at once, and this can scale more readily because you cannot use this import-export approach if you have a lot of areas, very complex capabilities for exchange between areas, etc. Eventually, we can extend this idea to nodal pricing. Instead of having two areas, you could say you have 3, 4, 5, and so on areas. And eventually, you could say that each node of the power system is one area, and you end up with nodal pricing. So this generalizes the optimization problem we had before. We have still the social welfare maximization, but when we look at the constraints, now we're going to have a lot more of this balance equation. You're going to have a balance equation per node of your power system. So if you have a power system with 1,000 nodes, you have 1,000 of these balance equality constraints. In terms of inequality constraints, you have the original inequality constraints for the schedule of consumption and generation, plus inequality constraints for all the possible exchange capability between each and every node of the power system. If you would like to look at some other discussion about nodal pricing, since here we don't really go into detail, I would invite you to look at this video, which in a few minutes describes everything about this idea of nodal pricing. Let's look at settlement now. I explained you before the basic idea of settlement when you have a zonal, but that would be the same for a nodal pricing scheme. It is that each and every agent receive or pay the price of the area where it is located. So if D1 is located on DTU West, it has to pay, the price of DTU West. D2 is located on DTU East, it has to pay the price of DTU East. D9 is located on DTU West, it has to pay the price of DTU West. Mathematically, you see, this relates to the equation we saw before for uniform pricing, except that we have an extra term here in superscript as an exponent. It's location. So you get the price, the market clearing price, but for your location being your area or the node of the power system you belong to. Same goes on the supply side. G1, which is on DTU West, will receive the price of DTU West. G2, which is on DTU East, will receive the price of DTU East. You may start thinking, is this fair or not? It is not about fairness, it's about respecting the physics of the power system and actually getting the price that relates to your local supply and demand equilibrium. As a consequence, the market here is not going to be budget balanced anymore, since the sum of the consumer payments may be greater than the sum of the supplier revenues. You may do the mathematics yourself for a case or for some other case, and you will see that. This difference is defining what we call a congestion rent, and this congestion rent is going to be collected by the system operator, if only one, or the system operators, for instance, if you have different system operators for different areas that are interconnected. This congestion rent is seen as a provision of money for future investment related to the power system. Thanks for listening. I would now invite you to use the self-assessment quiz to check your understanding.